This is SpaceTime Series 22, Episode 15. Coming up on SpaceTime. Goodbye, farewell and amen as mission end declared for the Opportunity Rover. Mining water on the moon. And discovery of a stellar flare 10 billion times more powerful than those produced on the Sun. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
One of the most successful and enduring feats of interplanetary exploration, NASA's Mars Opportunity Rover mission, has finally been declared over after almost 15 years exploring the surface of the red planet. The golf cart-sized six-wheeled robotic rover stopped communicating with Earth on June the 10th last year as a massive global dust storm enveloped the red planet, blanketing the rover's location and blocking out the sunlight needed to recharge the rover's batteries. Opportunity was expected to revive after the storm had passed, and its batteries would then be recharged from its solar cells. But when the storm finally abated and the dust cleared in August, the rover remained silent. Mission managers at NASA's Jet Propulsion Laboratory in Pasadena, California, believe OPI, as it's affectionately known, likely experienced a low power fault, a mission clock fault, and an up-lost timer fault, all due to the loss of power. It's thought that dust from the storm had covered its solar panels, preventing them from receiving sunlight. Normally strong Martian winds, which usually begin blowing around November, would have blown the dust off the solar cells. That then would have allowed the batteries to recharge and operations to resume. But the rover still remained silent. NASA tried sweep and beep commands designed to nudge the rover to send a response once the rover had powered up again. But despite more than 1,000 attempts to re-establish contact, Opportunity still hasn't phoned home. And so the decision's now been taken to formally end the mission. Originally designed to last just 90 Martian days and drive no more than a kilometre across the freeze-dried desert surface of the red planet, Opportunity remained operational for more than 14 years, travelling over 45 kilometres. Its final resting place, appropriately named Perseverance Valley, a gully leading off the rim of Endeavour Crater. During its mission, Opportunity revealed an uncharted Martian landscape, finding evidence that Mars was once a far warmer, wetter world, a world capable of supporting life as we know it. The final transmission formally ended a multifaceted 8-month recovery strategy, desperately attempting to compel the rover to communicate. Manager of the Mars Exploration Rover's project at JPL, John Callis, says his team have made every effort to try to recover Opportunity, but have now determined that the likelihood of receiving a signal is simply too low to continue. Opportunity landed in the Meridiani Planum region of Mars back on January the 24th, 2004, 7 months after its launch from the Cape Canaveral Air Force Station in Florida. Its twin rover Spirit landed 20 days earlier in the 166-kilometre wide Gusev crater on the other side of Mars. Spirit logged almost 8 kilometres before its mission finally wrapped up in May 2011. By that time it had become bogged in a sand dune with its solar panels facing away from the Sun. From the very day the two rovers landed, mission managers, rover drivers and scientists collaborated to overcome challenges and get the vehicles from one geologic site on Mars to the next. They plotted workable avenues over rugged terrain so that the twin 174-kilogram Martian explorers could maneuver around and at times over rocks and boulders, climb gravel-strewn slopes, probe crater floors, summit hills, and traverse what looked like dry riverbeds. In 2005, Opportunity lost steering to one of its front wheels. A stuck heater then threatened to severely limit the rover's available power, and ripples on a Martian sand dune almost trapped it for good. 2 years later, a global dust storm on Mars imperiled the rover before relenting. Then in 2015, Opportunity lost use of its 256 megabyte flash memory, and in 2017 lost steering to its other front wheel. Each time the rover faced an obstacle, mission managers back on Earth found a way to implement a solution that enabled the rover to continue its mission. Opportunity's final venture brought it to the western rim of Perseverance Valley. However, the massive dust storm which took shape in May and June of last year proved just too much. Opportunity's journey included a one-day Mars driving record distance of 220 metres, That was set back on the 20th of March 2005. OPI also returned more than 217,000 images, including 15 360-degree colour panoramas. It exposed the surfaces of 52 rocks to reveal fresh minerals for analysis and cleared 72 additional targets with a brush to prepare them for inspection with spectrometers and a microscopic imager. It found little round blueberry-like concretions of hematite, a material that forms in water at its landing site. The findings all supported the primary objective of the Mars Exploration Rover's mission, to seek out historical evidence of the red planet's climate and water at sites where conditions may once have been favourable for life as we know it. Because liquid water is required for life as we know it, Opportunity's discoveries implied that conditions in the Meridiani Planum may well have been habitable for some period of time in Mars's ancient history. Principal scientific investigator for the Mars Exploration Rover's mission, Steve Squires from Cornell University, says combining the discoveries of the Opportunity and Spirit rovers confirmed that ancient Mars was a very different place from the cold, dry, desolate world we see today.
This mission accomplished so much more than we wanted to. It's mind-boggling to me. We know more about Mars today than we knew 2 days ago. Both rovers together showed us that ancient Mars was much more habitable, was much more Earth-like than Mars is today. Mars today is a very cold, very dry, very desolate place where not much happens. If you go to the ancient past, compelling evidence for hydrothermal activity, hot water bubbling through the rocks, steam vents, water coming up to the surface, volcanic explosions, lots of impact craters. It was a hot, violent, steamy place. And it was the kind of environment that would have been suitable for some kinds of microbes. All of it very different from the Mars of today, different places that were visited by the two rovers, different from one another. And it sort of hints at the complexity that the entire planet must have. This was a great teaching tool. You know, it's been said many times that some of the most important scientific discoveries begin with the words, "That's odd." You know, you see something totally unexpected and then you follow it. To take that kind of immediacy of discovery and the true nature of science into the classroom, it was an opportunity to share with them science as it really happens. I work with engineers today who were 18, 19-year-old Cornell undergraduates at the beginning of the mission and actually built hardware that's on the rovers. There's hardware on the rovers that was built by Cornell undergraduates. They put their initials on it and everything. I can see by the career path they've taken, the trajectory that their career has taken, that opportunity early in the mission opened doors for them, at least in their own heads in terms of what they thought was possible for them. I mean, if you had told me around the time we landed that Spirit and Opportunity were going to each accomplish 1/4 or 1/10 of what they ultimately did, I would have been thrilled. And it's because of the longevity of the vehicles. You know, Spirit lasted 6 some odd years, Opportunity 14 and a half when we were designing them for 90 days. Mars just kept giving us new stuff. And so the payoff has been immensely greater than anything any of us ever in our wildest dreams conceived of. We have changed the way in which people perceive Mars. Every morning, you can open up your computer and you can go to a public website and you can see new vistas of Mars. They're always someplace new, and we're climbing mountains and we're descending into craters and these beautiful panoramas, and all of a sudden Mars becomes a place that humans can relate to, that you can imagine being. You've got these machines that are there that are built on very human scales, doing very human-like things. The kind of exploration that we do with rovers is very, very accessible. It's easy to understand. These are robots, they're looking at rocks, it's not that complicated. And I always felt that the unique accessibility of this mission gave us both a special opportunity and a special obligation to really try to share it with the public. And we've tried very, very hard to do that. And if part of the legacy of this mission is that a whole bunch of young people who saw that, thought that's really cool, but I bet I could do better, if that thought hit them and it helped to push their career in a certain direction, that ultimately could be possibly the most important part of our legacy.
That's Steve Squires from Cornell University. Of course, Mars exploration continues unabated. NASA's InSight lander, which touched down on the red planet in November, is now beginning its scientific investigations. The Curiosity rover has been exploring Gale Crater for more than 6 years now, and it's continuing to go strong. Nuclear powered using radioactive isotope decay, it doesn't need to concern itself with the threat dust storms pose to solar panels. And NASA's Mars 2020 rover and the European Space Agency's ExoMars rover will both launch in July 2020, specifically designed to seek out signs of past microbial life on the red planet. An armada of satellites are also orbiting Mars, sending back data on its atmosphere and spectacular images of the red planet's surface from orbit. But because of its perseverance, because of the fantastic images it provided and the new windows on Mars it opened up, Opportunity's journey will always have a special place in the history of Martian exploration.
To have positive confirmation of a safe landing.
We're seeing it on the LTP. Very strong on LTP.
Opportunity hit a hole-in-one when she landed. The airbag system rolled into this small crater called Eagle Crater. And when the rover first turned on its cameras, it saw that the rim of the small crater was lined with exposed bedrock.
So we took out our microscope for the first time and we took a picture, and the surface of Mars at that location is littered with an uncountable number of little round things.
That were called blueberries because they looked like blueberries in a muffin. What we discovered was that those are features that form in water, and they were a really definitive sign that there had been liquid water on the surface of Mars sometime in the past.
You know, after we left Eagle Crater, we went to Endurance Crater, and that's the crater we drove down in. And there we did what the geologists call an in-sequence stratigraphic section, which is essentially reading the chapters of the Martian history book in reverse order.
That rover became a stratigrapher. First time you had a stratigrapher on Mars. We knew we wanted to go after Endurance to Victoria.
We put pedal to the metal and we started heading there, tens of kilometers away. We had to literally surf across these dunes of wind-blown material, and the rover got stuck in one of those. We had to get the rover unstuck. What we found is the best way to get it out is just to put it in reverse and gun it. The rover eventually popped out. And so we changed our driving strategy. So we recognized these ripples as hazards. We get to this giant half-mile diameter crater, Victoria Crater, and we want to figure out, gee, how can we go into this thing?
All of a sudden we got high-rise images. We could see the rover in the image.
And that was the very first image that we got from space showing one of our rovers.
We spent a year scouting the edge of that crater to decide where we wanted to go in to get the best stratigraphic section.
We found a place to go in, and we drove down in, and we spent about a year inside Victoria Crater.
The science team was really excited about the idea of driving to Endeavour Crater, over 20 kilometers away. This is a long drive to do. It was going to take multiple years, but they decided to do it anyways.
There were too many of these dangerous ripples in our way, and we actually had to take this circuitous route that at times took us away from the crater, only to then cut back and then approach it more directly.
And then we pull up to Endeavour Crater, and all of a sudden there's all these new things to look at.
We first discovered the Homestake Vein. It was this very, very bright linear feature. It turns out that there was a big gypsum vein, and we see these gypsum veins now all over. So it was our first taste of what is a really important process on Mars.
We were driving to a valley, and along the way there we realized that right about the point where we were about to get to this valley, that was when we were going to cross the marathon mark. So we said, well, that's cool. We're just going to name this valley after that, call it Marathon Valley. That was when we reached the distance of a marathon, 26.2 miles on another planet. We continued driving through some slopes down a little bit on the interior of the crater rim until we came back out so that we could continue on to the next valley, Perseverance Valley,
where the rover was exploring when we lost contact.
We said we're going to operate this vehicle until the day where we can't, and that's exactly what we did, and I'm really proud.
We've set a foundation that will serve as the basis for future exploration.
And there you heard from Mars Exploration Rover Project Manager John Callis, Principal Investigator Steve Squires, Deputy Project Scientist Abigail Freeman, Project Scientist Matt Golombek, and Rover Driver Team Leader Heather Justice. You're listening to Space Time. I'm Stuart Gary. There's a new Australian project underway to mine water on the moon for conversion into rocket fuel. It all stems because one of the biggest problems with spaceflight, at least chemically powered spaceflight like we use here on Earth, is the cost of transporting the fuel needed for the journey. So, wouldn't it be great if you only needed enough fuel to get you there and could then fill up again for the return journey? And that fuel would be plain old water, one of the most common molecules in the universe. And there's plenty of it on the moon, frozen as ice on the permanently shadowed floors of polar impact craters which are never exposed to direct sunlight. Water molecules have also been detected in the thin layers of gas floating just above the lunar surface. Of course, water in the chemically related hydroxyl group can also exist in forms other than normal water molecules, by being chemically bound as hydrates and hydroxides to lunar minerals. And there's strong evidence suggesting that low concentrations of these hydrates and hydroxides cover much of the lunar surface. Finding water on the moon is important. Firstly, astronauts can drink it, they can break it down into oxygen and hydrogen and use the oxygen for breathing, and of course the oxygen and hydrogen constituents are also the ingredients of rocket fuel. Making rocket fuel out of water on the moon would significantly cut down the cost of carrying out space missions. Now, Professor Andrew Dempster and colleagues from the University of New South Wales are looking at the commercial viability of mining water on the moon to produce that rocket fuel. Dempster believes Australia is uniquely placed to carve itself out a niche in the global space industry by exploiting its position of strength in mining expertise to off-Earth mining. He says Australia has a natural advantage. It already has the world's best mining research, technology and automation tools and the planet's largest mining companies. The major deterrent for industry involvement has been the lack of understanding of the commercial viability associated with this type of project, and of course the perceived investment risk profile of off-Earth mining. Dempster and colleagues want to create the engineering machinery, mining methods, energy resources and communications required to make such operations viable. He says while commercial mining operations on the moon are still decades away, given sufficient funding, his team could be just 5 to 10 years away from piloting a water mining proof of concept operation on the lunar surface.
Any settlement that happens on the moon would need water for all sorts of purposes. There are people there, they want to consume it. If you're growing plants, you want to grow them. But most of the applications we're looking at for water at the moment would be before settlement happens, and so most of this would just be a purely robotic exercise. So things like if you can produce the water, you can separate it out into hydrogen and oxygen, you can then use it as rocket fuel. So you could then put that rocket fuel in orbit around the moon or in orbit around the sun, and so if you're on your way to Mars, you could refuel on the way. Now the reason why that's interesting is, or sensible, is that it costs at the moment about $10,000 per kilogram to get something into low Earth orbit. If you can create your water for less than $10,000 a kilogram, you've got a business case.
In order to do this, I guess there are various ideas. Are you going to melt the water in situ? Are you going to extract it as rock, ice rock, as in regular mines would? Or are you looking at extracting it out of the breccia on the moon?
Liquid water doesn't exist on the moon. There's not enough pressure. There are only sort of two types of water. It will either exist as a solid, ice, and then it will, if you sort of heat it up, it would immediately become gas. It will sublime directly to gas from a solid because of the lack of pressure. So what you need to be able to do is not only to heat the ice, but you need to be able to capture it and store it in a pressurized way that turns it into a liquid. There are all sorts of technologies that are around to try and do this. One of them sort of builds a bubble over the top of the regolith, which is the lunar soil, and you can apply heat to it and you can extract the water in that way and then gather it together into a container, pressurize it, separate it into the hydrogen and oxygen.
The technologies being looked at to achieve this, they're being experimented with now. Are you more interested in this, or are you more interested in the actual robotic, the autonomous vehicles that will be doing the extraction and then processing?
Well, we have a very wide range of interests. I mean, we have students looking at the ethics of this issue, how you might do an environmental impact statement, how you actually come up with business cases and how you can close them, which mining methods you might use to extract or to get the rock into a state where you can convert the ice into water, and mission design, how you look at the whole mission, where you put the resources, where you'd want to land, how you power the robots. So right across the range of research topics, we're looking at all of these things.
SpaceX are already looking at missions to examine the feasibility of mining at the lunar South Pole. Is this something you want to get on board with, or are you guys looking at a totally independent approach?
We're hoping to work with whatever partners or whoever would like to work with us. There are various companies at the moment. I don't necessarily want to name them, but some of the large international space companies have a very strong interest in Australia at the moment. partly because we set up our space agency last year, but also just because the space industry here is growing very rapidly, regardless of anything to do with the agency. We've gone from having 2 space startup companies 5 years ago to having over 100 now. It's a really exciting place to be looking at space, and that's attracting a bit of interest for some of these international partners. There's a logic to examining mining as a niche for Australia. We have the largest mining companies are based here. You know who they are, the BHPs and Rio Tintos of this world. We have the best mining researchers in the world here, mining engineering, and we have the strongest mine automation. So those mines up in the north of Western Australia where there are no people in the mines, they've been operating for a number of years now.
And successful trials with automated trains too. And they're like 32,000 tonne trains. They're not little things.
No. But to some extent, the degree of automation of those mines at the moment is not high enough to do in space. So by that I mean there's still a fair bit of communication between the mine and the headquarters. And one of the things that I'm personally quite interested in is the trade-off between how much communication bandwidth you need and how autonomous the robots have to be, how much decision-making they can do by themselves without having any intervention from the headquarters. So I think there's a lot of research to be done there as well.
Can you really compare mining on Earth to extraterrestrial mining, considering the distances, the different sorts of environments, and especially on the moon where dust plays such an important role?
The comparisons are probably more straightforward than you might initially think. The stages that you go through, what mining engineers call exploration and what laymen would call, lay people would call prospecting. They don't like the word prospecting, but when you talk about exploration in space, that means something else. So we need to come up with some language that's consistent. But that stage, the prospecting stage, the feasibility stage, then there's mining, there's transport, and there's delivery to a customer. A lot of that framework exists already for mines, and a lot of the big mining companies would understand how you go about putting together an argument for, or how you structure it. But we are not, though, talking about driving around with trucks with tyres twice the height of a person and those sort of things. It would be quite different mechanics, but at the high level it looks very similar. At the lower level it looks quite different. When you talk about the dust on the moon being a problem, that's absolutely the case. You need to have very highly reliable equipment. Maintenance is one of the things that is very important for terrestrial mining, even more so in space, because you can't send a person along to go and fix your robot for you. But when they talk about mining in a very remote place like the moon, the challenges are quite similar to, for instance, mining in the deep sea, in the deep oceans. So because, again, it has to be very remote, there's a degree of autonomy. There are environmental challenges. They're different challenges, but it's still the same general problem. So I think we've got a lot of clever people working on some of those problems already, and I think if we were to start looking at mining in space, we could then be learning lessons that we could apply on Earth.
Well, the United States is already looking at a successor to the International Space Station in the form of a new space station, which would be at one of the Lagrange positions between the Earth and the Moon. So it'll always sort of remain, though not orbiting the Moon, it'll sort of always remain in that position, and that would be a jump-off point for regular excursions, explorations, prospecting, whatever you want to call it, to the lunar surface. I believe that's where some of the first mining techniques of an extraterrestrial nature are going to be formulated and practiced.
Yeah. I wasn't going to mention the Lagrange point, but that's fine. That's actually, they're probably more likely to deliver these fuels to those points. And yes, we're getting quite a lot of interest in the US. They've named 9 partners that they would like to deliver payloads onto the lunar surface. Europe has been very active in their moon village. China has landed a rover on the far side of the moon recently. So there's a lot of international interest in the moon. I don't think we're being too way out there to be joining it in our own way.
What about a timeline? Is there one, or is that in terms of developing the technology, which obviously you're going to be doing here on Earth, is there a timeline for that, or is that too early in the process to look at those sort of things?
I think in terms of a fully operational commercial operation, we're probably talking decades rather than years. But in terms of proving the technologies to make that possible, I think missions can be put together now to start doing that. And part of what we're interested in at UNSW is really only examining technologies that are part of a closed business case. So if you say this is entirely commercially useful, this technology, then we'll study that one. I mean, an example was we had a student who was over at the Jet Propulsion Laboratory, and we've had 3 students have placements over there as part of this program, and he was looking at a Mars Mars settlement, and one of his early findings was if we use this particular technology and there were 40 people in the Mars settlement, 36 of them would have to be operating this equipment. And so clearly that's not feasible, and those are the sorts of things you want to knock on the head before you go start testing them on the surface if they're never going to be ultimately useful. So a lot of work has to be done ahead of time to make sure that what you're doing is going to be useful in the long run.
That's Professor Andrew Dempster from the University of New South Wales. I'm Stuart Gary. You're listening to SpaceTime. Astronomers have detected a massive stellar flare, more than 10 billion times as powerful as the biggest solar flares produced by the Sun. Stellar or solar flares are sudden eruptions of plasma and energy on the stellar surface. They're usually associated with sunspot or starspot activity and are often accompanied by coronal mass ejections. Flares usually occur when charged particles, mainly electrons, accelerated through magnetic reconnection, interact with the surrounding superheated plasma. On the Sun, magnetic reconnection occurs on solar arcades, a series of closely occurring loops following magnetic lines of force. These lines of force quickly reconnect into a lower arcade of loops, leaving a helix of magnetic field unconnected to the rest of the arcade. The sudden release of energy in this reconnection then triggers the acceleration of the particles. The unconnected magnetic helical field and the material it contains can then violently expand outwards, forming a coronal mass ejection. This also explains why solar flares typically erupt from active regions on the Sun, where magnetic fields are much stronger. The spectacular stellar flare observed in this story didn't occur on the Sun, but in the Orion Nebula, the largest nearby star-forming region to the Earth. Located just 1,344 light-years away, the Orion Nebula, also known as Messier or M42, is easily identified as the fuzzy middle star, fuzzy because it's a nebula not a star, in the sword of Orion. The nebula is a 24 light-year wide stellar factory with some 2,000 times the mass of the Sun. It's filled with molecular gas and dust clouds, which gravitationally collapse to form nurseries full of new stars. This is how our Sun and solar system would have formed 4.6 billion years ago. The massive history-making stellar flare the astronomers spotted, which lasted for several hours, is thought to have been caused by a disruption in the intense magnetic field activity actively funneling material onto a young growing star as it accretes mass from its surroundings. Observing stellar flares around the younger stars is new territory for astronomers, giving them fresh insights into the physical conditions in these systems. This flare was observed by astronomers using the James Clerk Maxwell telescope near the summit of Mauna Kea in Hawaii. The telescope's transient survey team recorded the flare using state-of-the-art high-frequency radio technology and sophisticated imaging analysis techniques. The original data was obtained using the telescope's cryogenically cooled Scuba 2 camera, which is kept at a frigid minus 270 degrees Celsius, almost absolute zero. The observation was part of a monthly tracking program by researchers around the world who used the James Clerk Maxwell telescope to observe nearly 1,000 nearby stars in the very earliest stages of their formation. The team's lead scientist, Dr. Stephen Mears, says the discovery of this magnitude could unlock decades-old questions about the origins of our Sun and planets, giving new insights into how these celestial bodies were born and a better understanding of the history of the solar system. You're listening to Space Time. I'm Stuart Gary. And time now to take another brief look at some of the other stories making news in science this week with a science report. It's been revealed that being pregnant during your teen years could have a cascading effect down your bloodline. A report in the journal PLOS ONE has found that the grandchildren of teenage mums tend to have lower school readiness scores than their peers. Researchers gathered their data from kindergarten teachers accessing 5 areas of child development. A new study has confirmed that Greenland is melting faster than scientists previously thought, and will likely lead to faster sea level rise thanks to the continued accelerating warming of the Earth's atmosphere. Scientists concerned about sea level rise have long focused on Greenland's southeast and northwestern regions, where large glaciers stream iceberg-sized chunks of ice into the Atlantic Ocean. These chunks then float away, gradually melting. But a new study reported in the Journal of the Proceedings of the National Academy of Sciences has found that the largest sustained ice loss from early 2003 to mid-2013 actually came from Greenland's southwestern region, which is mostly devoid of large glaciers. So whatever this was, it couldn't be explained simply by glaciers, because there aren't many there. Scientists think it's got to be surface mass. The ice is melting inland from the coastline. That melting, which is largely caused by global warming, means that in the southwestern part of Greenland, growing rivers of water are streaming into the ocean during summer and are likely to become a major contributor to sea level rise. A new study warns that native turtles in South Australia are facing extinction. The findings, published in the journal Scientific Reports, are based on research into native turtle populations in the Murray River and some of its associated waterways. Scientists from the University of Western Sydney found that species are in decline in the lower Murray River region and now completely absent from many locations across South Australia. Cybersecurity experts have uncovered a long-running clandestine hacking campaign being carried out by the United Arab Emirates. The operation, called Project Raven, is working out of a converted mansion in Abu Dhabi for the Emirates government cybersecurity outfit Dark Matter. It turns out this team includes more than a dozen former US intelligence operatives recruited to engage in the surveillance of other governments, militants and human rights activists critical of the Emirates. The hackers were using techniques gleaned from their many years of service with American intelligence agencies, employing state-of-the-art cyber espionage tools such as Karma to hack into the phones and computers of hundreds of activists, political leaders, and suspected other enemies of the Emirates, including Washington. Scientists have developed a new near-weightless material composed mostly of air, which is capable of both withstanding and protecting against some of the most extreme temperatures experienced in aerospace and industrial environments. A report in the journal Science claims the new ceramic aerogel performed well when heated to 900 degrees Celsius and then rapidly cooled to minus 198 degrees. Aerogels are a composite material made up mostly of air encompassed within a network of solid medium, such as ceramic, metal, carbon. Ceramic aerogels are incredibly lightweight and possess traits highly desired for enduring really demanding environments, like heat shields on spacecraft. The problem is most conventional ceramic aerogels are really brittle, and they're also susceptible to degradation due to extended high temperature exposure or large and rapid temperature swings, thereby limiting their use as a superinsulating material. The researchers say they resolved the problem by using atomically thin sheets of hexagonal boron nitride. A new study has found that the amount of time US kids under the age of 2 spend staring at screens every day has more than doubled between 1997 and 2014. But the findings reported in the Journal of the American Medical Association show that it's the good old television and not mobile devices which make up the bulk of screen time. The study, which used diary data collected between 1997 and 2014, showed that American kids under the age of 2 went from watching an average of 1.32 hours of screen time daily in 1997 to 3.05 hours a day by 2014. Researchers say that despite the fears about mobile devices increasing kids' exposure to screens, they found that most young kids under 6 spent most of their screen time watching TV rather than devices. You're listening to Space Time. I'm Stuart Gary, and that's the show for now. You can subscribe and download Space Time as a free twice-weekly podcast through Apple Podcast iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, from SpaceTimeWithStuartGary.com, or from your favorite podcast download provider. Spacetime's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., and available around the world on TuneIn Radio. If you want more Spacetime, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us on Twitter through @StuartGary, at Spacetime with Stuart Gary on Instagram, and on Facebook, just go to www.facebook.com/Spacetime with Stuart Gary. Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to Spacetime with Stuart Gary. This has been another quality podcast production from Bytes.com.